Complex numbers. Let's start with a review, and then I'll introduce complex numbers. If root 36 equals 6 and root 12 equals 2 root 3, because we take the 12, break it up, it's 4 times 3, so root 4 times root 3, so that becomes 2 root 3. Then what does root negative 36 equal? You're like, what? Well, if we break it up the same way we did the 12, root negative 36 would be root negative 1 times 36, which would be root negative 1 times root 36, which we know to be 6, but we don't know what this is, root negative 1. It's not real. Exactly. This is your new imaginary friend. Root negative 1 equals I. So we write it as just 6i. Something else that'll come up is I squared equals negative 1. And that triple equal sign means it's a definition. That's useful info for any future math majors, but the rest of us, With all this in mind, what would be root negative 12? And if you said 2i root 3, you're right. So here's our introduction to complex numbers. Complex numbers take the form a plus bi, where a is the real part and bi is the imaginary part. Let's add and subtract. Well, if you remember, 2x plus 3x would be 5x. So then what do you think 2i plus 3i would be? 5i. And 7x minus 4x is 3x. Then 7i minus 4i would be 3i. Wow, adding and subtracting i's works the same as x's. It's just another letter. We're actually collecting the coefficients, the numbers in front of, so it doesn't really change what we're doing. So then 4 plus 2i, a complex number, plus 7 minus 5i, another complex number, should work the same as 2x plus 4 plus negative 5x plus 7, right? Notice that they're switched in positions, because complex are a plus bi, but we tend to write polynomials with the x terms coming first. Yes, with only a formatting difference. In polynomials, the x tends to come first, but in complex numbers, the imaginary term always comes second. So if we take the imaginary, or the two complex numbers, 4 plus 2i plus 7 minus 5i, we get 11 minus 3i. Removing the parentheses first, which is very similar to 2x plus 4 plus negative 5x plus 7 would be negative 3x plus 11. The only real difference is that for polynomials, we put the x term first, and for imaginary, for complex, we put the imaginary second. How about multiplying? Now, this actually is 15.9, multiplying complex numbers, because 15.8 was really fast. It was just, what is a complex number and how do we add or subtract? which is very similar to adding or subtracting polynomials. Multiplying works the same with a slight twist at the end. So multiplying polynomials would be the same as multiplying complex numbers with only a slight twist at the end. So if 2x times 3x is 6x squared, then 2i times 3i would be 6i squared. Almost. If you remember, I squared is defined as -1. So this is the twist. When you're done multiplying, you need to convert all I squareds into -1. So now it becomes not 6 times I squared, but 6 times -1, which gives us the -6. So we multiply the i's just like x's, but at the end we get that little twist. We got to take all the I squareds and make them -1 and then simplify. Likewise, 4 minus 2i times 5 plus 3i. If we FOILed it out, we'd have 20 plus 12i minus 10i minus 6i squared. Collecting the i's in the middle would give us 20 plus 2i minus 6i squared. And now remember, the I squared is -1. So now we've got 20 plus 2i plus 6. Got to collect the 6 back with the 20, and we end up with 26 plus 2i. Again, it's not any harder than multiplying polynomials. The only difference is that when we're done, we're not quite, because we have to take the I squareds and make them -1 and recollect. How about dividing complex numbers? This is also from 15.9. 4 minus 3i all over 2 plus 5i. Yeah, that looks hard. Let's use a skill we already know. Let's try a technique similar to rationalizing the denominator, which we used with roots. Remember this from last class's review. 5 over root x plus 2. To rationalize it, we just took that plus sign in the denominator in front of the 2, change it to a minus sign, put it on top and bottom. So we multiply the top and the bottom both by root x minus 2. Because what that does in the bottom is it creates a difference of 2 squares. And we end up with x minus 4. Then we just have to do the top. So we use the same technique. So what would the conjugate of the denominator 2 plus 5i would be 2 minus 5i. All we're doing is changing the sign on the imaginary part. The imaginary part. So let's actually do it. So we've got 2 plus 5i in the denominator. So we're going to use 2 minus 5i. So we're going to multiply the top and the bottom both by 2 minus 5i. So on the bottom, we're going to get a difference of 2 squares. The 2 squared minus the 5i squared. The full 5i being squared. And on the top, we just have to FOIL that out now. So on the bottom, we get 4 minus 25i squared. And on the top, we get 8 minus 20i minus 6i plus 15i squared. Collect like terms on the top. And now we're going to convert all our I squareds into -1. So the 15i squared becomes 15 times -1, and the 25i squared becomes 25 times -1. So now we've got 8 minus 26i minus 15 on top, and on the bottom it's 4 plus 25. So we end up with negative 7 minus 26i over 29. Not hard, just tedious. Got to be methodical. Identify the conjugate of the denominator, multiply top and bottom. You've got to do some foiling in the top, set up the difference of squares in the bottom, collect like terms, and then turn all your I squareds into -1 and recollect.